Hello everyone and welcome to a new episode of All Things IDA. In today's episode we're going to continue working on the PE file format and in particular the export directory. We're going to learn how to manually parse the export directory and interpret its contents. This is very useful when dealing with shellcode and importless PE files basically. This will help us understand how shellcode still manages to resolve and import stuff from external modules. So by learning how to interpret the export directory, we will be able in future videos to understand how shellcode works and so on. So with that, let's get started. Okay, so for this video, I can no longer use Wizmo since it does not export anything. Instead, I picked a random DLL from my system and loaded in IDA using the file loader. Even though now we didn't manually load it, we can still continue with our exploration of the PE file format. So when we loaded this file with IDA, with the file loader with IDA, IDA already mapped the sections and the contents correctly to the virtual memory. So this is the thing we did manually, the first video. And now by loading it using an IDA loader, we're not really taking out the fun, we're simply saving some time. In future episodes, we're gonna implement a loader from scratch to get us back to that state that we are using right now. We have the header, we have the imagent header as usual, and optional header, and in the optional header we have a bunch of directories. If you remember from last time, when we went to the image optional header, for example, which is part of the file header, and we said we have 16 data directories. And the first directory is the export directory. Second directory is the imports and so on. So we want the first directory, which is basically this one here. So the same, this is virtual address and the size. So the first directory will take us to the export. Let's just change the way the image data directory works like we always do. So we're going to change the virtual address representation to be using the image base as usual. And like this, it will show as a nice RVA. So now all the RVAs, and let's also change the display here for the size to be decimal. So now we have the first directory, it points here and so on. We don't care about the import. Now we're going to focus on the first directory, which is the exports. So let's follow it, that directory, and it takes us somewhere. Now that somewhere has a very clear structure. And if we also look at Ange's illustration here we have the PE file, we have the header, we have the optional header, and we have the data directories. And here, as we said, the first directory is the export, second directory is the import. There are 16 directories. For the export, if we follow it, so following the export here, it takes us to an image export directory. And that's the format that we're going to be exploring, the image export directory. And here, this is basically a descriptive table of the fields in that structure. So in IDA, that structure is called image underscore export directory. So let's apply it. I did already export that type, so I have it. So just to double check, image export directory. I do have it here. So here we will put side by side. This table here is basically describing the fields here. So first thing is let's apply the image export directory to that field and interpret it. So Alt Q, image export directory, and here we have it. And let's call it IED for image export directory, expanded. So what do we have inside an export? So when the DLL says I have something to export, what do we have? So we have characteristics. So here it says reserved must be 0, timestamp, versions, and here we have the name of the DLL. So this is the name of the DLL and it says it's an RVA. So same story here. I already converted the name representation instead of being a D word. So let me corrupt it for a second. And here we got rid of the name, but the name was an RVA. So we'll have to simply change the representation, make sure it's image base, or we can put the base and apply it. And like this, we did this many times before, we revealed the names. What comes next is base here. Base is called base, but in reality, what we're looking at is ordinal base. This is just a number that when we export functions by ordinal or by number, not by name, then we will have at least a minimum base for those ordinal numbers. So for example, if the ordinal base here is set to 2, that means there is no exported symbol that has an ordinal below than 2. Could be 2 or above. By default, the numbering starts with 1. So if I go to kernel 32 here and go to the image export directory, we can see here in that example in kernel 32, the base is 1. And like this, if we take a look at what IDA already parsed for us, all the functions have ordinals 1, 2, 3, 4, starting from 1. And in this example, if I open IDA's export view, so our goal is not to use IDA's interpretation, but just to show you, we're gonna open the exports window and show you that the ordinals here, they start by 2. They don't have to be consecutive, so they can start by 2 and assign another number later on, but that base is what sets the starting point. And this is something for the user. Internally, the ordinal number is used as an index in a table, and it should be 0 based. So what we're gonna do, if the user passes us an ordinal base, say give me resolve a function by ordinal number 2, we take what the user gives us and we subtract the base, and now we're back to find me function with index 0 essentially. So that's the base. Next other important field is the number of functions. This is very important. This tells us how many functions we have in that PE file, how much we exported. So if we want to work the export directory, we have the count now. So we just go over the count and interpret them accordingly. So here we have 23 functions. So those 23 functions here, when we look, we see 22. Why is that? Because we can have gaps. And those gaps are useful if we want to have non-sequential ordinals. So we leave a slot and we put a null pointer. That means although we have an entry, it doesn't resolve to anything. This is just to let us really control the ordinals. So let me show you what I mean. So here we have number of functions. That means how many functions how many entries we have. If they're all non-null, that means we export 23. But here clearly IDA shows us that we have 22. And how come we have 23? So let's continue for a second. And we explain why the discrepancy between 22 here and 23 here. So to explain that, let's skip number of names for now and look at address of functions. So address of functions is the export address table. This is where the exports live. So here we have 23. And that's actually the table here, address of functions, which is again in RVA in the export. So here, if we go to address of functions and revert it back to regular RVA representation, we have address of functions. It's not accessible, it's in RVA, right? So we'll have to do the same stuff I've done before. Whenever we have RVA, go fix it in IDA to have a better representation. So the address of functions is a RVA table. So this is it actually. It just happens to be below the IED. So we're gonna follow it, make a DD, change it to user defined offset, make sure it's using image base, or we can just put it ourselves, and then apply for the first member. Like this, now we reveal the function table. These are all the exported functions. And we can make an array of 23 entries. And let's keep one element on a line. Let's display the index in decimal. And that should be good. So here, notice those entries. Entry 18 and entry 9. 19 and 18, they are 0. 0 plus image base gives us image base. So while we don't see they are 0 directly, let me show it to you in regular non-RVA view. So let's just turn those back to regular dwords, and you'll notice at 18 and 19, they're 0. That's why we skip them. So we skip 2, and we should have, instead of 23, 21, but IDA shows us 22. It's just because of the DLL entry. It is considered in IDA as an entry. Export window in IDA is the entry points window, basically. So these are all the entry points. They're not explicitly mapped 100% to actual concept of an export table. So consider entry points to that module in IDA's point of view. So we we have two missing entries, and the DLL start is considered an additional one on top of the regularly exported ones. So you see here, these are the two entries. We have to account for that. So if we scan the table and we see a null, we have to skip it. Let us make those again, Control R, and shows them nicely. So here we have, these are all the exported functions. And IDA knows the name for now because I loaded it in IDA. But if we're doing this from scratch, we will just have a name. We'll have a dummy name. We won't have something useful. But since IDA parsed the file and discovered the names and so on, it gave a name to that address. We're gonna learn how to figure out the names. So now is the time we go back to what we skipped. So number of names. So we know what is number of functions and the table, which is basically address of functions. That's the table. EAT, that's the table, export address table, all the exported stuff. For the names, as we said, we could export by ordinal or by name. And so here what it is telling us that we have 11 names. That means the rest are by ordinal. And again, just skipping ahead, we can see here, for example, we have those entries. 3 entries, they don't have a name. More than 3, we have a lot of entries, they don't have a name. So let's sort by name. Here we have 5, 6, 7, all of those are by ordinal. So if you want to resolve them, say get proc address, and we pass an ordinal instead of a name. So that's why we only have 11 names. Once we say we have 11 names, now in the image export descriptor, we have the actual names. Where are the 11 names? So let's follow the table. So here we follow the names, and here as well it says address of names, which is here, name pointer RVA. It's the address of the exported names relative to the image base, RVAs. So let's follow the address of names. And we should have 11 entries because of the number of names that are RVAs that should point to strings that are the actual export names. So let's follow it. And here we can make a D word. We have 11 elements, so we're gonna make an array 11, display indices, etc. These are the RVAs for the names. Let's simply remove the regular D word and make it RVA. So Control R, use image base, make sure it's gonna be resolving to 64-bit address. And here we have it. So here we have one string, here we have another string, and so on. So this is how we got the names. We still have one more field, the ordinal table. What's the ordinal table? So here let's call this, let's say export address of names, and address of name ordinals. This is a bit tricky, but it's important. So that's where we have that mechanism of translation to be able to serve either by name or by ordinal. So let me explain how that works, the address of name ordinals. First of all, this table, ordinal table, we should see that the ordinal table has the same size as the address of names. They're parallel arrays. Address of name ordinals, if we follow that, we should have, since the ordinal is 16 bits, we should have here a DW, which is a word, a single word, of 11 elements. This should contain the ordinals. So let's first make a DW, make an array. Here, Ida guessed correctly 11, and accept. Here, let's make H. Now, let's explain this table. How those two tables, address of names. So here, let's say export address of name ordinals. I want to explain to you the relationships between address of names, address of table, and address of functions. So address of functions doesn't know anything. It just say, you know, I am a table, I'm an array, I have those indices, and I'm gonna put the functions here. That's it. And now if you wanna look me up, you have to give me an ordinal or a name, do some computation, and then retrieve an index, use that index in the function table. So let's do this, for example, let's follow the address of names and take a look at name number 9, index 9. So in the export address of names table, we have WAB open. The string is in that table, in the address of name table at position 9. We take that position and then we use it. We go to the second table now. So we found the name index in the address of names. Second step is take that index and see where it stands in the ordinal table. So remember number 9, we go here and we go to index 9. The value at index 9 is 0. This is telling us that to get the actual position in the address table. So here 0, here EAT at address 0 got us WAB open. Let me take a scenario where I want to resolve by ordinal. So suppose I'm given ordinal, the user says resolve ordinal 10. So let's see how we can get from number 10 to the actual address. We're not gonna cheat, we're gonna verify at the end that it's gonna resolve to this. So our starting point is an ordinal. Because we didn't start by a name, we were given an ordinal. So we're given ordinal number 10. We go to our export direct. The user gave us 10, the unbiased ordinal. Unbiased meaning we take the actual ordinal base. So we have number 8. The user wanted to resolve 10 minus 2, 8. We don't have a name, we just have an ordinal, index number 8. Now we have no choice but to consult the table directly. So we don't have to go through names or anything in this case. We just have an index, but we unbiased it. So index 8. Here, index 8. If we follow index 8 in the address table, it should give us the same address. Here, 7A, 7F0, 7A, 7F0. Okay, so let's pick another name. One more example. I'm gonna pick on a new group W. I have this name. Resolve it for me. Great. So you're looking by name. Okay, let's go to the address of names. Look for that name on new group W. On new group W. Aha, it's at position 7. Great. Now we have the ordinal. We take that. We go back to our table address of ordinals. We go to position 7 and the entry is 12. Now we have that entry 12. Now we go to the address table and we take number 12. And here on new group, that's the one. I'm gonna now explain a bit other PE files and discuss some corner cases and so on. Let's take a look at this DLL I found on my system. Let's see what is peculiar about this one. Let's go to the export directory. So look at this one. This is really interesting. We have 2,783 functions. We have 33 names. If we look at what IDA gives us, indeed, we do have this much functions, but only 33 of them are exported by name. So let's try to sort by name and see if we can find something by hand. So let's say this one. Orthogonal line position, for example. So we go to the address of names. We look for that. It should be, since we have 33 names only, so we should find it easily. So here, I think this is the one orthogonal, and it is at position 24 in the names table. We go to the mapping table. Here, entry number 24, this one. This is the ordinal, because we're looking at the ordinal table this time. We take that and we simply go to the address of functions table and go to that index. Here, this is the one. This is the index. We found that export. Now, one thing to talk about, here we have different stuff in IDA. So IDA, for convenience, changes the icon. If it's something pointing, so we can export functions, we can export anything, we can export variables. We just have an address basically. That address could be pointing to data or text. So for convenience, what IDA gives us is just show us that export lays in a data segment, so not code. So we see the D here. And if the exported address is in a function, we see the F. One more thing before we start to write the code, I want to talk about forwarding. So we have a case where we have forwarded APIs. So for example, here, sometimes we can say, okay, I have kernel 32, heap unlock, but heap unlock is not implemented in kernel 32. Instead, it is forwarded. So how do we know if we're dealing with forwarded or not? Let's take a look again. What's the actual concept? So we have to go back to the data directory. Data directory has two entries. We have the RVA and the size. Therefore, we have the range. So here the export directory is really 432, which is 1B0. So let me begin selection, go to 1B0, just for illustration purposes. This is the whole image export descriptor pointed by the data directory. Now, if we are dealing with a function that is not implemented in the same DLL, it's forwarded. The way we can tell if it's forwarded or not, when we follow the function implementation. So when we go to the address of functions. So here we have address of functions, and those functions should basically point to the implementation. So the implementation normally should be either in .data or .text. For forwarded cases, if the pointer to the implementation lies within the data directory of the export, that means it's forwarded. So just to give you an example, this DLL in particular doesn't forward anything. So the function pointers are pointing outside that green area that I highlighted. So they're not forwarded. I know for sure kernel 32 has forwarding. So what I did here to illustrate for you, I did the same and colored the whole thing. So this whole range is the export data directory size. Now, to detect forwarded functions, all we have to do is when we evoke the address of functions, if one of those RVAs points to within the actual export data directory, that means we're dealing with a forwarder. So let's take a look. So let's pick here alloc console, for example. Let's follow it. Look at this. Alloc console seems to have an implementation, is in kernels is .text. But on the other hand, if we pick entry number 18, for example, in the address table and resolve the RVA and look at the RVA still lies within the data directory. And because of that, that means it's forwarded. And by convention, we can say the DLL that we're forwarding to dot the actual implementation where the forwarder happens. So that's how we can detect forwarded exported items. So one more thing here, let me pick another DLL. Let's see if anything is peculiar about this one. This one as well, that's another example here. We have the same story, name, ordinal base is 1. We have 16 exported functions. We don't know really if all of them are exported or there are gaps, there are null entries. And we have just 2 that are exported by name. So let's interpret this one again. If we open the exports first, just to double check. So we do have 17, 16 plus the entry point. This is the way IDA displays it. So no empty elements. So we have 2 exported by name. Let's follow them. We go to the address of names and we have at index 0, we have can unload, and at index 1, we have get class object. Now in parallel, let me look here on the side at address of name ordinals and look at this, how they're related. So here the parallel arrays, as we said, index 0 is pointing to the can unload now. So we now know that DLL can unload function is at index 0. Go to the ordinals to index 0. We get number 4. Number 4 is the actual entry in the EAT. So we keep number 4, consult the address of functions table, seek to number 4 position, and here we have resolved can unload, which we got from the address of names, we got from address of name ordinals, took it back all the way to address of functions. So it's a bit of a dance. We have to consult a couple of tables depending on how we're resolving. Okay, so I think we are now ready to write some code, and hopefully with writing the code, this should make things clear. The goal is to have something similar to the exports. We will be able to print names if they exist, the implementation address, and the ordinal. As usual, we have to go to the image DOS header, empty headers, data directories in order to reach this vital point, image export directory. And from there, we can start doing our work. I'm gonna open the snippets window. To save some time, I prepared this code and I'm gonna explain it. So we're not gonna hard code any address because I'm gonna take that snippet and run it in another DLL and show you how it works. We have covered already how we work with opcalls as typed objects to make parsing structures easy in IDA. So I create a typed object for the vital structures. DOS header to take us to the NT header. So basically the progression is a DOS header, NT header. Within the NT header, we'll have data directories in the optional header. And from the data directory, we pick data directory 0. That will take us to the export directory. So I prepared all those nice typed objects for retrieval. And my main function takes a base. Give me an image base, and I'm gonna parse your exports for you. First thing is we retrieve at the base what we expect as the DOS header. After we get the DOS header, remember we can go to the NT header following the ELFA new. So we take the DOS header, plus the base takes us to image NT header address. From the image NT header, next step is to read the whole header. So we say image NT header type dot retrieve at the virtual address of the NT header. This will give us the whole image NT header. including the signature, file header, and optional header. Now we want the first data directory. Export IDD, image data directory. Just take a copy, is the image entity header, optional header, data directory 0. We took a copy of the parsed export data directory. And finally, we're really approaching, this is what we want. We want to reach to the image export directory. So we are almost there. Here, once we got the directory object, we simply break it into the directory start with basically converting the directory's virtual address to a full address, and get the size of the directory, get the IED end, and start. Then, now we know where is the image export directory. What I did here is simply copy it. And we're just gonna test it real quick by printing what I retrieved. So we have image export directory, and from it we got address of functions. So this is going to be address of functions. So it's gonna be the EAT. So it's gonna display EAT at funcs EA, and this should give us correct information. So let's run it. So it says EAT. Indeed, this is where the EAT starts, and we have 23, which is this one. As well, to save some time, I'm gonna paste some code and explain it. So once I get all the prerequisites, so this is almost boilerplate code, or maybe up to this point, nothing really special. Now going afterwards, so here. So what I did here, just for caching, I created a table, names table, which is a dictionary and ordinals. What I'm going to do is go over the address of names, which are parallel. So they have the same number of entries, which is number of names. So if we have number of names, which means there are some exports by name, at least one, it makes sense then to go over both name ordinals and names. So here what I'm doing, I'm simply getting the full VA of the names EA by using address of names. Then I go one by one. So I go to the address of names and dereference every RVA. So we get the words of the names EA, and then use just I times 4 since we're dealing with the D words, plus the base gives me the actual name, one name at a time, per name. And all I'm doing here is simply in that dictionary, I'm putting the name, I'm getting string literal contents of the name, I'm reading wherever the name points at, get the string and cache it. So now if you ask me what string we have at index 0, I have it for you. And similarly, I'm also accessing the ordinals table and doing a reverse lookup. So here, the ordinals table, to help me with the names, what I'm saying is, let's dereference a given ordinal. So here, let's dereference every entry, every D word. We can see here the get D word, and put it in the dictionary and reverse lookup. So instead of saying index 0 equals 16, I'm gonna say index 16 is add 0 and so on. So far, this is good for what comes next, because this is not useful. It doesn't have any address information. It just have ordinals and names. Now let's go over the address table. So what we want is address of functions and also the number of functions. So we're gonna work number of functions over the address of functions table. And then for every index, we're gonna consult the appropriate tables to get the names. So let's do that. So here, this is what I'm doing. I start a loop with the number of functions. So here we have 23, and we're gonna walk one by one. And that table, what we have is just an RVA pointing to something. We don't know what that something is. And indices. So those indices are important because if we can link them back to ordinals or names, we can associate a name to that entry. So let me show you how we do that. So we go over all the 23 entries in that table. That table doesn't give us any name information or anything, just table of addresses. So here we dereference the first entry. I got it as a D word. Now, if that D word RVA is 0, then skip it. Otherwise, function EA is the RVA plus base, and the ordinal is wherever it is in the table plus the ordinal base. So this is just for information. At the minimum, I know there's a function with this ordinal, and it's implemented here. That's all I know. Now, we need to know if we can have a name ordinal table. Do we have something? Do we have an index for the name table? If I have the index in the name table, then I'm gonna be using it to get the actual name. So we get the name index. Now, before using the name index, I do that check to see if the pointer at the address at the functions EAT if it's inside the EAT range, I'm gonna say it's forwarded. Let's forwarded. Let's just say forwarded. How did I know? Because the function resolution still sits within the image export directory. If that's the case, I have the name, which is the name is gonna be pointed by the function entry here. It's not gonna point to actual body of a function. It's gonna point, as we said, to. So instead of having, this is kernel32, which does have forwarders. Instead of the func EA pointing to actual implementation, the func EA points to a string describing where it is forwarded to. And that's exactly here what we did. We take the function EA as a string this time because we know it's a forwarded one. And we get the name and we simply display, okay, I have the function ordinal. This is not really the function EA, but this is where the forwarder string exists. What's the original name? The original name is simple. So here we got the name index. From the name index, we can get back the name table. And the name table can, given an index, gives us already computed name. So here I'm saying, okay, I have the name index. And say names table, give me the name and also display the forwarded name. If it was not forwarded, then we have two cases. It's either -1, that means it has no name entry whatsoever. In that case, I'm simply saying, okay, I have a function and it has that ordinal. And remember, I already biased that ordinal by adding the ordinal base. If it had a name, great. This is where it's implemented. This is its ordinal. And this is the lookup for the name that I got from the table. In fact, the lookup is mentioned here in the pseudocode in the documentation. So we do have to consult those two lookup tables in order to actually get the results we want. So putting this whole script together like this, where we parse everything, cache the tables, and then interpret the actual entries, let's see what's the output here. We should have similar output to the exports window. So should have very similar output. And if not, we might have a bug. So let's run the script and see the result. So I'm gonna run the script and it's starting to tell me like how much and so on and so on. But most importantly, we can tell here WAB open is correctly shown as ordinal2 from our code, and also the name is correct and the address seems to be correct. Entry 5 as well as 360. So this is working nicely as expected. So what I'm going to do, since this is just a single snippet, no need to use the snippet manager, I'm gonna paste this in this peculiar example, which has 288 entries, but the majority are null. Let's see what happens here. So let's paste this code. Let's run it. So it's not gonna match IDA. As we said, IDA will always add one at least for the main, but here let's see. So here we do have 28 and here we have 27. So we are correct. And just like a quick spot check, for example, let's say ordinal 302, it should be add service indeed, and so on. So having done that, actually, let me show you something cool. So let's try this. Let me try to run calculator and start a new instance of IDA and attach local Windows debugger. Let's find calculator. Any application, doesn't matter which one it is. I'm gonna pick an address and see if some address, say Twin API, and jump to module base. Okay, so we can, for example, take that same snippet, and instead of the image base of our main module, here we're just looking at something in memory. And out of curiosity, what I'm gonna do is simply use the same logic we did to display all the exports and their implementation addresses from memory. Yeah, so here I got an error. I have to do some setup, right? So I have to include all the proper headers for the type information library. Hopefully this should work now. Let's try. Okay, so I brought in all those types, so we can actually create a typed object, and I run it. Let's see what we have, and we can also compare with IDA's view. Here, for example, ordinal 1. Here we have twin 1. That's it, correct. Get metro mode, ordinal 8. Get metro mode, and so on. All right, so this concludes our video for today. We illustrated multiple cases of different kinds of exports. We also learned how to enumerate the exports, how to interpret the ordinal numbers, fetch the names, skip empty slots, and so on. And that will come in handy for the future. And with that, I'll see you next time. Thank you.